Hello everyone. In today's talk, we'll have a look at how agentic AI leverages harnesses and pedagogical thinking in order to deliver tailored and learning science-grounded supports to students. Recently, the application of generative AI and large language model into education has been very impressive, from creating course material to personalized learning support and personalized learning tasks. However, most current AI system has no representation of the learner. It doesn't know if the student has been struggling for 3 weeks. It doesn't know if the last 5 answers were wrong. It doesn't know whether to give a simpler explanation or a harder challenge. It doesn't plan ahead for the students. It just knows from the session and a drifting model of a user. What we need is a system that knows where the student is in their learning trajectory. It detects risk before failure happens. It assigns intervention levels based on the student need. It grounds every decision in learning science, not intuition, not probabilistic inference, but based on theory. To illustrate the harness, we'll look at these four popular learning theories. First, we have Vygotsky's zone of proximal development. The core idea is that every learner has a zone where they can succeed with support, but not by themselves. Your job as a teacher or as an AI is to pitch instruction right at the edge of that zone. Too easy and nothing is learned. Too hard and the student shut down. The ZPD is that productive middle ground. We are going to spend most of the case study on this one. Next up, we have Bloom's taxonomy. It describes cognitive tasks. Cognitive tasks are not at all equal. Recall is easier than application. Application is easier than synthesis. The system enforces it as a hard constraint. It will never assign a synthesis task to a student who can't yet recall the basics. The ceiling is stored in the knowledge graph, not left to the large language model to guess. Next up, we have Keller's ARCS model. Um, Motivation matters. A student who is bored or anxious learns nothing, regardless of how well designed the content is. ARCS breaks motivation into four components: attention, relevance, confidence, and satisfaction. We measure all four. When confidence drops below a threshold, the system sends encouragement. When relevance is low, it reframes the concept with a real-world example. Lastly, we have spaced repetition. Memory can decay. If a student masters a concept today and never sees it again, it's gone in 2 weeks. The review card note in the knowledge graph schedule revisit based on how well the concept was retained. The timing is as important as the content. The four theories tell us how to teach individual students. The RTI-MTSS framework tells us how to organize intervention at scale. RTI stands for Response to Intervention. MTSS stands for Multi-Tiered System of Support. They come from special education research, and they've been proven to work throughout K-12 education as well as university. It is consisted of three tiers. The wide base, tier 1, covers about 80% of the student. This is high quality instruction for everyone, adaptive pacing, and spaced repetition. So in our system, this should be handled automatically. Tier 2 consisted of 15% of students. This is the group of students that need something more targeted. Small group strategy, supplement content, and closer monitoring. The pedagogical agent detects the student using risk score and escalate them or de-escalate them depending on how well they perform in the class and how often they use the system. Tier 3, the top 5%. This is a group of students that need individualized intervention plan. This is also where the human teacher get more involved because at the tier 3 intervention, AI is not enough. Pedagogical quality is determined not by the large language model itself, but by the quality of its surrounding harnesses. Large language model is not magic. A large language model that receives a bad prompt gives a bad response. If it is constrained by pedagogical rules, learner state, that large language model can become an agent. The three pillars below show what a harness is made of. First, we have the prompt architecture, which ground the theory in every call. The knowledge retrieval, which is structured facts from a graph and not hallucinated knowledge, not hallucinated advice. And the decision constraint, the rules that govern when the large language model is called and what it's allowed to do. At the center, we have the core language model. Everything surrounding it is a harness. Starting from the top, we have the prompt architect that shapes every query before it reaches our LMM. The learner state encoder converts raw student data into a structured representation, such as zone classification, scaffold level, ARCS scores, before any decision is made. The pedagogical knowledge graph is created for theory-grounded facts. The RTI MTSS constraint engine enforces tier rules. If a student is in tier 3 escalation, the large language model informs the teachers. The SHARP and LMM explanatory module generate rationales after decision. And the outcome feedback loop closes the loop. Every response feedback into the student's model. The question is, should we store the pedagogical knowledge in a knowledge graph or in a LMM prompt template? The table shows the trade-off. Knowledge graph gives you consistency, interpretability, and explicit theory encoding. Learning science rules become curable graph relationships. Prompts template give you flexibility and faster iteration, but they're sensitive to the wordings and hit context length limit. So the answer that we reach is that we use both of them. The knowledge graph handles structured rules such as prerequisite, zone threshold, and the Bloom taxonomy ceilings. The prompt template handles flexible multi-step reasoning, such as generating a work example, reframing a concept, scheduling tasks. Neither tool is used where the other is better. So the roles of the large language model here is just not to generate text. They plan, select, and calls tools. Most of these tools are completely deterministic, and let's have a look at them. They're separated by 3 levels: scaffolding, by zone, and by motivation. Uh, by the scaffolding level, the agent reads the current scaffold level from the student model and selects the right tool. Level 3 means they need full support, generate a work example, then a guided problem. At level 2, we generate a flashcard and a quiz with a hint. At level 1, we just give quiz without hint and a spaced repetition reminder. And at level 0, we give them assessment item without any support. So as we can see, as we go down the level, we take away the scaffolding, and throughout that we make sure that the student retains the knowledge and just not just relying on the large language model to give them the answer immediately. Secondly, we got separation by zone. If the student hits frustration, the agent cone escalates to tier 2. If the student reaches the mastery level, we can unlock the next concept. And if they're in the zone of proximal development, we select a scaffolding level appropriate, and we go back to the column 1. And finally, we got the motivation. The AISC run in parallel. If confidence drop, we can send them encouragement. If the relevance is low, we can reframe the problem to generate a real-world example. And after any outcome, for example, if the student become more interested or less interested in engaging, we can update the student model to know whether the method that we're using is working or not. Let's have a look at how Vygotsky zone of proximal development get integrated into the agentic AI. So we have 3 zones. First, we have mastered. This is the area of concept where the student has already know most of this. They can do this alone without external help. And on the right hand side, we've got this frustration area, which is even with help, they can succeed. And further instruction or exercises does not help, but only discourage them. And in the middle, we have the ZPD. This is where the learning happen, where they can um, achieve learning with scaffolding and support from the teacher. So in general, that we will always try to pitch the instruction inside the ZPD zone. We provide scaffold, then gradually remove the scaffold as the accuracy, as the, their responses to the question get better, the performance in the class get better, and once they reach a certain amount of accuracy, we move that concept to the mastered area and advances to the next concept. And if they fail too often, then they enter the frustration area. Then we escalate that and don't generate more content, and we will revisit that later. So how do we encode this into Agentic AI? So first we have the intuitive limit, which represent the mastered area. Second, we have the delta epsilon limit, which is the current concept that we're studying, the one in the ZPD zone, shown in the purple. And lastly, we got the continuity zone, um, which is up until the delta epsilon limit is mastered. The arrows between them are the prerequisite edges. A student cannot enter the ZPD for delta epsilon limits until they have mastered the intuitive limits. And that's hard enforced by the cipher query, and it's not by the prompt. And that is a key distinction, because if a prerequisite ordering live inside a prompt, it could be forgotten, overridden by a persuasive student message, or just simply wrong on a particular inference. In the graph, it is a structural constraint. The large language model never sees its choices. It's already been made before the large language model receives any input. The concept node for the delta epsilon limit doesn't just exist in the graph, it is carried through the properties. These four properties are the ZPD encoded as data. So we got the ZPD entry threshold at 0.7. The student accuracy and the prerequisite must reach 70% before they enter the ZPD for this concept. Below that, they're not ready. The mastery threshold stays at 0.85. Once the student hits 0.85 accuracy on this concept, we determine that they have mastered it, and then we can advance them to the next concept. And third, we have the frustration signal, and we set this at 3 consecutive failures. And finally, we got the Bloom ceiling in ZPD. And while the scaffolding is active, the maximum cognitive demand is understanding. We don't necessarily ask the student to synthesize or evaluation tasks until the mastery is confirmed. So inside the zone of proximal development, we just ask that the student understand the concept. And then once that got moved to the mastery level, we'll begin to give them tasks that involve synthesizing and evaluation. So next, we will explore the scaffolding fading. The student, so let's say for example, the student is currently at level 2, marked with the triangle. This is the area where they provided partial scaffold. They've been here for a few lessons, and the accuracy is climbing over time. At the level 3 full scaffolding, the tools are creating work example and creating guided problem. The large language model walks the student through a complete solution before they attempt anything. At level 2, a flashcard is shown first, then a quiz item with one hint available. This is still providing partial support, but not directly hand-holding the student. And once the student has mastered the concept more, that we move them to the minimal support. The quiz has no hint. There's also spaced repetition reminder firing from the review card, reinforcing concept the student has seen but hasn't fully cemented yet. And at level 0, we provide them with no scaffolding at all. We give them unseen assessment item. If they get it right, then we can confirm that they have mastered the concept. So this is just one particular example of how we might implement the scaffold fading. If we expand more on it, we can create more like exercises, more tools for the agent to invoke, so we can get a more complete understanding of where the student is on their journey. The scaffold level is a variable in the student model. The large language model does not decide it. As accuracy climbs, the system decrements the level automatically, and the large language model receives the current level as context and produces content calibrated to that level. Okay, so in this slide here, I just put everything together in one graph. The student node represents the student state, and so their current understanding. They're connected to the intuitive limit with a mastered nodes, which means those topics inside the intuitive limit is marked as done. The connection between the student and the delta epsilon limit is marked as in ZPD, and this is the active learning target. The prerequisite change runs intuitive limit to the delta epsilon limit. So that means that the student need to master the prerequisite knowledge inside the intuitive limit group before they can move on to the concept inside the delta epsilon limits. And finally, we got the continuity, which is locked by the delta epsilon limits. So ZPD is just one of many learning theory, one of many learning science concepts. If we zoom out a little bit, we can see that each implementation or each query chain has a particular learning science theory attached to it. We can see here the student is connected to the AISCS state mentioned earlier. Just a quick recall, the AISCS state represent the student motivation. It stores the confidence and the relevant score. When the confidence drops, the tune orchestrator calls the tune orchestrator can give a signal to signify that the student needs more encouragement. And when the relevance is low, it can send a signal to the generator to tell them that the example needs to be more relevant to the student interest. The review card, this is connected to the space repetition theory, and even though the student has mastered this concept, the space repetition schedule keeps it alive. And next we have the ZPD rules, which is connected to the delta epsilon limit. This is the area of learning that we are targeting. And finally, we got the Bloom taxonomy level. It is connected to the continuity. When the student is ready to advance, the system already knows what cognitive level the next concept requires. And the pattern is identical for every theory: a node type, a relationship type, and queryable properties. Adding extra learning theory or adding extra pedagogical practice into this system does not require rewriting any prompt, but it does require adding more nodes to the system, adding more node and relationship, and the harness query picks them up automatically. And finally, the way that we know that this is working is through three lenses. First, we need to evaluate the agent quality. Does the React loop behave correctly? Does tools get called at the right moment? Is the generated content faithful to the intervention plan? These are measurable with benchmarks such as agent bench and tool call logs. And second, and probably the most relevant to what we're building, is the pedagogical alignment. Does the content respect the Bloom scaling? Do intervention decisions follow the RTI MTSS rules? Can educator read the sharp explanation and trust them? This requires both automated rubrics and educator surveys. And finally, this metric is the most relevant to the system, which is the learning outcome. This would require longitudinal grade trajectory measuring across many deployment and many years. So we need to detect risk detection F1 score, completion rate across cohorts, longitudinal grade trajectory. This metric only become meaningful after pilot deployment. And on a closing note, just 5 things to take away. First is pedagogy must be designed in, not added on. The harness is the system, and the large language model is just a small component inside it. Two, the RTI MTSS model provides the decision logic. The large language model provides content based on that logic. Three, the knowledge graph stores theory as queryable data. Adding a new theory means adding node, not rewriting prompts. Four, the agent is a tool orchestrator. Most tools are deterministic. Only content generation touches the large language model. And five, explainability is not optional in education. Educators need to understand why the system made a recommendation before they will trust it. That trust is load bearing. Without it, the system doesn't get deployed and doesn't see production. All right, thank you for coming to today's talk.